All right. Once again, it's time for me to address one of sort of like the timeless questions that math teachers seem to end up facing. Where are we going to use this? So we spent the last two videos talking about measures of dispersion, in particular calculating the variance and then the standard deviation of a data set. The issue that ends up coming up is we've spent a while on the methodology. We haven't had a chance quite yet to talk about what it actually tells us about a particular data set. So in the slides, I mentioned, well, one particular use for it is you can sort of use it as a means of comparing one data set to another, assuming they have some reason to be compared. Um, the big thing is looking at it as a measure of consistency in your data in some sense. So, for instance, suppose I were teaching two sections of the same class, and I give those two sections a similar test. So, while in trying to figure out which class did better on the whole, using something like the class mean on the test makes sense to tell me which section was performing better. The standard deviation on those test scores, however, might give me an idea as to how closely packed together the scores were. The catch is it's a little bit backwards from what you might expect. So remember, if you're thinking of standard deviation as measuring how much the data differ from the typical, it kind of stands to reason that you want the standard deviation to be lower in that instance. So the smaller the S value, the more consistent your data. So higher mean would be better performance. Lower standard deviation would mean more consistent performance. So I also like to talk about this in the context of thinking about like sports examples. So we've talked about win totals. So barring any weird accidents or ties or something like that, generally speaking, the average number of wins from one season to the next in a sports league should be the same because they play the same number of games and somebody wins every one of them barring ties. So they should always have the same average number of wins, but you could actually use a standard deviation on the win counts as sort of a measure for consistency inside the league from one season to the next. Sports pundits will often talk about league parity. You can kind of use standard deviations from year to year as a measure of that parity as time goes on. So you can use them as a basis for comparison. Awesome. What if you don't really want to compare a data set to anything else? What if you just want to look at the data set on its own? What does standard deviation give us in that instance? So it turns out you can also use standard deviation sort of as a sense of, in a sense of how the data are clustered together, or how tightly packed they are, if you think about it in that sense. The idea there is imagine that you kind of plot all of your data points like on a number line, and then imagine, sort of setting up brackets along that number line. It's probably better if I draw a picture for this, right? So I'm going to draw a number line out right here. And imagine sitting in the center, we've got our mean, x bar. All right. So what we're going to do is sketch this out using brackets, and we're going to measure out how wide those brackets are based on our data set standard deviation. So I'm going to kind of use the standard deviation to walk backwards in this direction and to walk forwards in the other direction. So that would look like x bar minus s in the one direction. Over here in the other, I would have x bar plus s. Okay? And then we can look to see how many of our data points, if we were plotting them on this line, end up falling in this window. Does that make sense? I hope so. I mean, you can't tell me. So let's look at this in the context of those test examples that I've really just about ground into powder at this point. So our mean was sitting at 82.75. And we worked out that the standard deviation in that case was 14.51, as I recall. So if we subtract 14.51 from this guy, that drops us back to 68.24 in that direction. And if we add it over here, that takes us up to 97.26. All right, if you look back at the test scores, if you've got them listed in notes or whatever, pull up, I think they show up in a thumbnail for one of the other videos, wherever you get them. Looking to see how many of those scores end up falling in here. The only one we're missing is the very lowest, because it was like a 53, and then the very highest was a 98, which would just be like barely hanging around like outside this. So within one standard deviation, we have 6 out of our 8 scores. So 6 out of 8, or if you were wanting a percentage, 75% of our data scores lived within one standard deviation of the mean. You might also, be willing to try to kick it open a little bit further. How far are we if we go 2 standard deviations away? So that would look like x bar minus 2s, and then on the other side, same thing, but with a plus. All right. So now, if I subtract another 14.51 from this guy, so you can think of it rather than worrying about the 2s, just kind of iterating additions and subtractions by the standard deviation, I got the 53.73 going in that direction. And back over this way, I think it's 111.77. I think that's right. Yeah. So now at this point, I've grabbed the high value, the 98. I still haven't quite gotten to the lowest because, like I said, it was a 53. So within 2 standard deviations, I have 7 out of 8. Or if I'm doing my arithmetic correctly, that would be 87.5% of my data values live within 2 standard deviations of the mean. You might want to go out one more standard deviation to push this out another bracket in each direction. I don't have quite enough space on the board for that. But needless to say, if I move out another 14.5, I've grabbed that final test score, and it turns out I have all 8 of my test scores, or 100%. Okay? So that's one example of this stuff in action. So I've got in there, I've got another example I want to take a look at. Like I said, I like to get maximum mileage out of these things. So bear with me. I'm going to clean this up. I'm going to use the same number line. But let's go back and look at the guys who signed the declaration. Okay, so got stuff cleared off here. So looking at the slides, I went ahead and did you a favor, cranked out the mean and the standard deviation for the ages of the 56 guys who signed the Declaration of Independence. The mean that we came up with there was 44.9. Again, yeah, this disagrees from what we did in section 4.2, but remember that mean was an estimate because we were working from our frequency distribution. If you actually worked out what's going on for all 56 numbers, that's what you get. Okay? Okay. The standard deviation, I promise, I've checked it, I've double checked it. 10.9 is the value for S that we end up getting in that instance. So now, if I do the same thing, I subtract 10.9, I add 10.9, well, that drops me at 34 on the nose. Over here, it would be 55.8. Okay? So that's why I ask how many of the ages ended up falling between 34 and 55, and include the 34s in this instance. So if you got the handout where we did this before sitting beside you, great. When I counted it up, I got 38 out of the 56. So that works out to be 67.8% in total if you round off to the nearest percentage. So that's one. You go out another standard deviation in each direction, well, that's 23.1 right there. And then over here in this direction, that would give me 66.7. Again, adding 10.9 to this, subtracting 10.9 from that. All right. Looking back, we've now grabbed everybody because the youngest age we had in that list was 26. It turns out the only 2 we're missing at this point are the very last 2. We had a 69 and a 70. So that would be 54 out of 56. And assuming I did my arithmetic correctly as a percentage, that's 96.4% of the data. Like with the test scores, if I did this one last time and tacked another bracket out on each side, I grabbed the last 2 ages because I would be up at 77.6, I think. So I have all 56 ages, 100% of them, if you want to be a little pedantic, living inside that window. All right. So the last thing I wanted to mention before we wrap up talking about dispersion, you may notice these patterns that kind of end up building up. So I mentioned for data sets that I call nice, so air quotes, trying to lean in here, nice. We'll talk more about what nice means when we deal with our final section of course material. But for those nicely behaved data sets, there are some kind of expected percentages you expect to see there. So I had it listed as 60. I was gonna say for a nice data set, 68.27% live within one standard deviation. Within two, you'd expect 95.45. Within three, it's just about everybody, 99.73%. You'll often hear people just describe it as like 68, 95, 99. So yeah, we'll talk more about what that nice means when we get to our final section of statistics material next week.